Hello, welcome to the second lesson of the dark matter module of this school. I'm gonna now be a bit faster regarding the properties of dark matter to win some time for later on in the most technical part be slower. Dark matter has to be dark, we said already, it has to be cold. Cold means that the particle is the dark matter has to be non-relativistic, and this is required because if you have relativistic particles and they interact only through gravity, they don't generate bound structures, so they cannot generate these halos or these other properties making dark matter grow structure in the universe if they are relativistic. So it has to have some speed, okay, which is smaller than the speed of light, okay, much smaller or at least smaller, okay, certainly non-relativistic. The reason why we call this cold is that if we have a particle which has been produced thermally, meaning that it has some thermal structure, some thermal spectrum, it is when the temperature is below the mass that this typical velocity is smaller than the speed of light. Otherwise, remember that the temperature is giving you an idea of what is the typical kinetic energy, and if the temperature is bigger than the mass, right, that means that the typical kinetic energy corresponds to particles which have to be indeed relativistic. So if it is smaller than the mass, then the kinetic energy is mv squared over 2. So then the typical kinetic energy for temperatures smaller than the mass corresponds to v much smaller than the speed of light. For these particles, there is a bound that can be applied, which is that particles which are thermally produced cannot be more massive than kilo electron volts. Right? So the maximum mass of these candidates is it's this one, and this is because since temperature is evolving with time as the universe expands, it has to be non-relativistic, so it has to be satisfying these conditions for large enough time, right? So that means that if particles are not satisfying this bound, then they are not gonna generate this growth of a structure, if you want, for enough time. Okay, this is a bit a hand-waving argument, but it is the way to understand it for now. This bound is not always applicable, for instance, for axions. Okay, they are not thermally produced. We'll discuss it in a couple of videos, and that means that they can violate this bound enormously. So they can go to masses as low as 10 to the minus 21 electron volts, which is quite small. The next thing about dark matter is that it has to be stable. That means that it has to live for at least the order of magnitude of the age of the universe, 13 giga years, not giga electron volts, of course. And this is because it has to act as a dark matter cold source for enough time to go from CMB, remember, to today's structure. So we know that it can decay, it's fine, but not fast, right? And indeed, also, you can try to find its traces, so it can decay into ordinary standard model particles. This has been looked for in many observables, but never found. The important point is that if whatever decay channel it has to stay with us for at least 13 giga years. All right, I think that also means that when you build a candidate, typically in BSM models, it's hard to build a BSM, well, not hard, but you have to be careful on how you build this dark matter candidate. You need typically a symmetry for this particle not to decay fast, right? Which happens with many particles of models beyond the standard model. In particular, supersymmetry, if you want to have it with a certain dark matter candidate, you normally impose what is called R parity, and in other scenarios like with extra dimensions, something called K parity, and so on and so forth. Dark matter should also be non-baryonic, okay, meaning that it cannot be composed in principle of particles of the standard model. You would say that, how do we know that? Right? Because in principle there can be states of the standard model which are dark, not maybe in a star, they can be maybe somewhere in the intergalactic medium or somewhere. Well, there is a very interesting observable in cosmology, which is having to do with what is called Big Bang nucleosynthesis. So in cosmology, there is a way to generate the isotopes the atoms that we see around us, the helium, hydrogen, lithium, and so on and so forth. And this is going through some nuclear reactions that are very sensitive to the amount of protons, the amount of electrons, the amount of nucleons around. So you cannot generate them in the right amount if you assume that there are more baryons than the ones we observe. In other words, there is a quantity called omega baryon, which is basically the energy density of baryons divided by this energy density that we used already when we were discussing the CMB probe for dark matter. So remember we discussed omega C, omega called dark matter, and it turns out that the observable of nucleosynthesis, so the amount of hydrogen, helium, and other elements, already tells us that the amount of baryons in the early universe can be at most be 1/5 of the amount of cold dark matter that you have in the universe. Okay, so unless there are some exotic states that were present in nucleosynthesis, okay, from the standard model, but there are no candidates like this, at least not simple ones. So unless they were already exotic by then, it's impossible that you can satisfy that omega B is equal to omega cold dark matter. Another candidate in this category is the possibility that there are black holes of standard model particles, but you have to generate them very early, and generating black holes is not something simple. I'm just going to put it there. Okay, so it's hard to have dark matter made out of baryonic dark matter. Dark matter has to be also collisionless. What does it mean? Remember that we had before made this picture of two halos going one against the other and generating a structure. Okay, I'm going to go upstairs of this form, where this halo going to the right after some time is here and this other one is here, so no halo, galaxy clusters, while the gas remains in the middle. That means that the blue dark matter has gone through basically without interacting, so it has traversed almost as transparent medium each other, so the collisional cross-section cannot be big, and there are bounds that you can put on this self-interaction, and typically are of 1 centimeter squared per gram. This is the units that astrophysics like for this observable, when you take the cross-section divided by the mass. Okay, cool. So we have many knowns about dark matter, but they are not so good, in the sense that even with all this information, we don't know anything about the fundamental properties of dark matter. We don't know the mass, we don't know the spin, we don't know the charges. We only have bounds of all of those. We have some knowns, and I already told you some of them. For instance, we know that if it is thermally produced, the mass has to be bigger than kilo electron volt. Okay, well, that's something we know. So some candidates are going to be excluded by this. We know that if the dark matter is bosonic, then the mass has to be bigger than 10 to the minus 21 or 22, depending on which article you look at. Let's do 22 to be conservative, electron volts. Where does this tiny number comes from? Well, it comes from the fact that dark matter, as any other fundamental particle, has to satisfy the principle, the Heisenberg uncertainty principle, right? You can write it as you want, h bar. Let's just do h bar, okay, on the sake of simplicity. Okay, let's put it like this, 2 pi h bar. So if you have a galaxy which has a certain size, okay, then it has, and this candidate has certain wave spread in momentum, mass multiplying velocity. Since the velocity of these galaxies cannot exceed what is called escape velocity, which is the velocity that would make this state leave the galaxy. So these states have to, remember, I'm thinking about a dark matter halo with a certain size and made out of particles. And these particles, the de Broglie wavelength, okay, is basically the mass multiplying by the typical velocity. But these velocities cannot be big enough, large, arbitrarily large. Otherwise, they would escape from this bound structure and they wouldn't be generating this dark matter halo. After some time, they will all fly away. That means that delta P, okay, is as most mv escape. And from these properties, if you plug them here, this is what you have to do in the exercise. You will see that you find this bound. If you apply them to the objects which are smallest and dominated by dark matter, which are called dwarf spheroidals. Okay, that's very interesting. So you have two things we know about dark matter. Another one, similarly, if dark matter is fermionic, okay, then the mass has to be bigger than around 400 eV. And in this case, again, this is an exercise. The argument is the following. It has to do with the fact that delta x delta p is always the minimum size of phase space for any particle which satisfies quantum mechanics. Has to be this one. But galaxies, okay, again, has some size in x, some size in p, okay, and in this volume, okay, if you fill all the states one by one, how many states there are that you can fill? So number of states imagine that you take a galaxy as a square, and you're going to have size of the galaxy cube multiplying by the maximum p that you can have. What is the maximum p? Cube. And all this has to be divided in small cubes of 2 pi h cube. Okay, so the minimum size. So this is the amount of, if you want, phase space number, so the number of states that you can have in a certain dark matter halo, right? And when you plug numbers here, and you take into account that all these states have to explain the total mass of the dark matter. So imagine that all of them are filled. So this has to be the mass of the galaxy. I'm being a bit fast here because this is an exercise. Okay, don't worry, you have to think about this. If not, there will be the solution. So you put all of them, and you know the mass of the galaxy. In the exercise, I give you density and volume. Okay, once you put this together, you find that the mass of the fermionic candidates cannot be smaller than 400 electron volts. Okay, so those are knowns about dark matter. Not so spectacular, but still there are some things we know. Finally, if dark matter are made of black holes, then there are many other bounds that you can put. So there are bounds of the cross sections. There are bounds. I wanted to put just cross-section independent bounds. So those are absolute bounds. All right. So let's now, after this first part of the module discussing properties of dark matter and evidence of dark matter, we're going to jump now into a more technical part, which is thermal production in the early universe. Which is going to bring us to what is called the WIMP miracle. All right. Very good. So we have seen that there is a strong case to introduce this new particle of dark matter. Another question is, where does this particle come from? In the case of the WIMP, weakly interacting massive particle, there was a bit, well, there's still some excitement, and there was more in the past, because there is a mechanism to produce it very, very naturally if you take into account the physics of the early universe that we already is already well established. And this is based on thermodynamics, particle physics, so quite a broad topic, and general relativity. Okay, so putting all this together, there is a way to understand how particles are generated. So there is a cosmogony telling us how particles are generated in the early universe, right, from certain rates and from certain expansion of the universe, from certain universe histories. Okay, and this can be used also to understand the amount of ordinary particles that can be produced, and those are very successful, like in the Big Bang nucleosynthesis I discussed before. The amazing thing is that they are also very successful to accommodate the production of the most popular dark matter candidates, okay, the WIMP dark matter. So it is natural to explore first this way, and afterwards we will explore other ways to produce dark matter. All right. So as I said, this is going to be a bit more technical, and it will last this and maybe also the next video. Yeah, I hope you enjoy it. So first, let's discuss the physics in an expanding universe. So if we are in general relativity, it happens that if you have a collection of mass which is isotropic and homogeneous, it either expands or contracts. It's not stable. That was puzzling for Einstein and for many others, and it drove to what he called his biggest mistake, the introduction of the cosmological constant. But it is what it is. It is, if we believe in general relativity, this is a fact. So the universe is indeed isotropic and homogeneous when you look at it at large scale. So if you look at the universe, of course there are structures, there is you and me, there is this, the Earth and everything, so everything looks very different in different directions. But if you look at the scales above megaparsec, so you average over megaparsec scales, the universe looks almost the same everywhere and in every direction. So the universe is homogeneous and isotropic at megaparsec scales. Yeah. So once you have this, you can understand, as I say, all these megaparsec scales as a kind of medium, okay, like the water, or the air, all right, and let's study what happens with them. So in this medium, you can define the different distance between the average volumes of the universe, okay, x, okay, and then the expansion, if it is the same in all directions, cannot be dependent on which particular direction you're looking at. So that means that the time dependence on how this is evolving has to be a common factor that we call the growth factor, okay, and then just distance at a particular time. Okay, again, because this we know that the galaxies are gonna, well, at this scale, are gonna either expand or contract, but this doesn't depend on which direction or when in the universe this happens. This should correspond to a common factor in front of the typical distance, between these two objects. So you have two objects, and you look at them at a later time. Yeah, they either expand or contract, and as I said, this evolution is parameterized by a function that doesn't depend on where these two objects are living. Okay. So, yeah, if you think about volume, the same. So this is volume at a particular time, and this grows as a different time, and it kind of grows in a kind of homogeneous way. Very good. So that was the law. This is the law for the expansion of the universe, for the position, and now we can define the velocity. Now, what is the typical velocity of one galaxy with respect to the other? So just take the time derivative of what you had before, and you will find that that easily, that it is a dot, it is 0, and here the position of the oops, sorry, the position of the position at a particular time. If this is today, if this 0 typically means today. What does it mean? It means that the velocities of galaxies which are farther away are linearly dependent with the distance. So they are faster and faster receding from us as you go farther and farther away. And this has a name. This is called the Hubble Law. It was discovered in the data of 1930s by Hubble, and it is one of the main discoveries showing that the universe is indeed expanding, and it is homogeneous and isotropic. It's expanding, and it should be expanding as homogeneous and isotropic. Then this number here, okay, is the rate of expansion, and today it has a value, a dot over a today, of 100 kilometers per second. It has these units per megaparsec multiplying little h. Remember that we introduced already little h. I didn't tell you what it was before, and it is, as I said, a way to easily do and remember what this quantity is, okay, without having to be very precise. So this quantity is around 100 kilometers per second or per megaparsec, and the only thing that you don't know is h, and h from data is around 0.7, okay, 0.67, 0.71, depends on which survey you look at, and there's some controversy about today about what it is, but this is basically what it is, the order of magnitude. All right, so what determines this expansion rate in the universe? Well, this is when you have the only place where you have to use general relativity is to write this law, okay, which is called Friedman Equation, and that relates the expansion rate of the universe to the total amount of energy density in the universe. Okay, here it is. Remember that gravity is sourced by energy densities, by momentum in general relativity, and that means that if you try to expand or contract, this law is going to be precisely given by the energy density that you have in place in this particular case. So here it is, energy density. So here we have, oops, sorry, I have to, there was an interruption, sorry. So here we have this Friedman equation, and I was saying that the energy density now is what determines everything about the expansion of the universe at this stage, at this level. Now, how do we continue? Well, we can now understand something we introduced before, that was the rho c. Remember, we have introduced it a couple of times. So rho c corresponds to precisely putting here nothing but the current, okay, today. The current values of the expansion in the universe, okay, and this is the value that I don't write it, this is in the notes, and that we have used to normalize what the energy densities of other species are. Okay, something which is also useful is the definition of redshift. So redshift is a way to give a time for cosmological evolution, which is more appropriate to cosmology, and is basically giving you the rate between the universe today and the size of the universe, in the sense of the typical distance between galaxies, or well, objects at large scales. Okay, so this ratio is what is called redshift, and it has to do with the fact that the light also in general relativity redshifts at this according to this quantity. Why this is more convenient than time? Well, because instead of talking about 13 billion years, 14 billion years, the redshift between today and, for instance, the Big Bang, or not the Big Bang, but the CMB, when the CMB was released, which is 13 billion years, in redshift is around 1000. So it's always more natural to talk about these units, which are more appropriate to, and also they are more physical, right? Because they are giving you an idea of physical things, like, for instance, the size of the universe today as compared to the size of the universe when something happened. All right, so the next thing is going to be exploring what are these energy densities for different situations. So energy density, for instance, for non-relativistic particles. So what do you want? You want the energy per unit volume. Energy is going to be, for a non-relativistic particle, mass multiplying nothing, the mass basically, and the volume. What is the volume? Well, the volume is going to be a cube, if you want, and whatever L distances you are talking about. So if there is a volume, it expands, say, right, remember that all the distances are multiplied by a factor A, one and a different rate state in the cosmic history. This is going to be A2L. This is L. So the energy density for non-relativistic matter is this one. For massless particles, or for relativistic case, the only thing that changes is that the energy now is given by the momentum, or if you want, the 1 over the wavelength of this object, and sorry, for relativistic, and as you stretch this wavelength, because the universe is expanding, the momentum also is modified, right? This is the intuition that you can verify this intuition with the more complicated algebra, but this is what happens. And indeed, P, the momentum, also evolves at 1 over A to the 1 over A. So the energy density for relativistic species behaves as energy over volume, so 1 over A divided by A to the cube. So it evolves as the universe expands as A to the minus 4. Okay. So this means that if there is some radiation in the universe, some relativistic or radiation today, so at a certain time, when the universe has some size, as we go back in time, the universe was smaller, so the universe is currently expanding. So here the universe was smaller, so you have some radiation. The way it evolved is with A to the minus 4. If there is some non-relativistic matter, like dark matter, for instance, it goes like A to the minus cube. Yeah, this is not, of course, properly done. I just want to exaggerate the effect. And it's already telling you that when you want to solve Friedman equation, remember the equation upstairs? Okay, at late times, the typical thing that dominates are non-relativistic species, but at early times there is the relativistic species that dominate. By the way, there is also a connection between what I just said about the momentum scaling as 1 over A and what I told you before, that the temperature of a distribution evolves like indeed also 1 over A. And the reason for this is that when you have a thermal distribution, let's say of photons, let me do it down. What do you have here? Well, you have the standard Bose-Einstein distribution, and if P, so as photons evolve, the distribution did not change, and as P goes at 1 over A, you can also realize that this means that T goes at 1 over A. Again, this is something that is not, I'm not going to prove, but this is indeed what happens when you study how photons propagate in an expanding universe. All right. There are other species in the universe. There is dark energy, and in the case of dark energy, rho is constant, which is quite an amazing thing. Even if you expand, you don't dilute. So this is why that dark energy is such a difficult medium to reproduce with the ordinary matter, because if you expand something, typically the energy dilutes, but in the case of dark energy, it does not. And more physically, there are species which are produced at high temperature, so they behave as relativistic, and this is then the typical distribution they have. But then at some point, the energy, okay, which is given by, in the case of relativistic, by the momentum, at some point the temperature drops, okay, so much that now this whole thing, and the momentum also redshifts to the level that energy is now given by the kinetic energy. And you can prove that, well, if you take the distribution with these two limits, it means that when the temperature is much bigger than the mass, then this corresponds to the law of rho going at 1 over a to the 4, and when T is much more than the mass, indeed, again, all this can be done consistently, and this is what we expect. So before I just told you, like with these hand waving arguments, which are more or less real. Well, they are real, they are correct. If you want to do the whole thing systematically, it requires more effort that is not worth for this course. Okay, this is what is called kinetics in a expanding universe, and it can be a bit complicated. All right, so this tells us, if we know the amount of relativistic particles and non-relativistic particles, we know, so if we know rho, we know how the universe expands. Very good. But this is not what we want. We want to know, well, we want this, but we also want to know how particles are produced and how do they behave when the universe is expanding, how the rates are behaved, how reactions happen. Okay, this is the kind of question that we want to understand now, and this is what we're going to start exploring today, and we will continue tomorrow. Okay, so we're going to now explore thermal equilibrium in an expanding universe. Okay, it's going to be, it is 3.2 in the lectures. How does this happen? Well, we're going to do some kinetics, so it's a fascinating part of physics, and we're going to do some simple stuff, And the first object that we need to introduce is the phase space distribution function. Okay, which has the following meaning. So this function multiplying d cube x d cube p, and well, normalized by 2 pi q, sorry, h bar cube. This is nothing but the number of particles with momentum p plus delta p and at x plus delta x. All right, so this is what it is. So you go to a region of space, okay, and you want to know how many particles there are there. Is basically multiply fx p t by this number, and this will be the particles with a certain momentum. If you want to have all the particles, what do you have to do? Well, you have to integrate, so all the particles, you have to integrate fx p t by all possible momenta, no? Right? Yeah, I say no sometimes, sorry. So it's gonna give you the number of particles in this little volume. If we now want the number of particles per unit volume, okay, which is in cosmology, everything is normally per unit volume, because volumes are so high. The important thing is that really what happens locally at each particular region of space, not really what happens globally. So the number of particles per unit volume, well, it is basically what I just wrote, this integral p, sorry, here, dq p, and you want to have them in the little volume. So you have a volume, so you want to have the total number of particles in all the volume. You have to also integrate over the volume element, yeah, and this is, well, normalized by volume. Okay, now what is the energy density per unit volume? Sorry, the energy per unit volume, the energy density, it is going to be precisely, well, what you had before, but now you have to put the energy for each particle. So each particle carries some energy. Here, number of particles in this little volumes, two integrals over volume. Okay, so this is the way you define the energy density. Sorry, I think that today I'm having some problem with my software. Anyways, that's the way we define the energy density. And now what we want to know is, what is this distribution? So this distribution function is something that in principle has to be computed given the different processes in the universe. But if we are having an equilibrium configuration, we know from thermodynamics that the distribution function first is not going to be space dependent, because we assume that the universe is homogeneous and isotropic. So you can forget about this space dependence here. So let me cross it. And in momentum, okay, it's going to correspond to one with the distribution function from thermodynamics, which are only characterized by energy and by chemical potential. So let's forget about chemical potentials for now, and let's simply write it as energy. Depending on fermions or bosons, we find these different signs here. Once you plug this back into these equations, you find some very important thermodynamic quantities, well, that are not new for this module. So energy density of bosonic particles if they are massless. So if E corresponds to P, energy density is nothing but pi squared over 15 t to the 4. Fantastic. And this indeed is already telling us that we were on the good track when we were saying that the temperature scales at 1 over a, because remember that we know from other arguments that this piece behaves as 1 over a to the 4, and t behaves as 1 over a to the 4, as 1 over a, so this also behaves as 1 over a to the 4. So all the logic we followed before makes sense. Remember how does this energy density evolves with time. Similarly, you can compute the number density of photons. So let me just give you what it is. And here it is important that there is a difference between fermions and bosons. So G effective is 3/4 for fermions, and it is 1 for bosons. Okay? So all these are properties that, again, you can compute simply by solving the integrals that I showed you before. Now, for a massive particle, the energy is basically the mass and plus a kinetic energy part. So the leading part is the mass, and in this case, rho is m energy multiplying n, right? And the number density, again, you can compute it by using this expression of the mass in the distribution function and back into these two quantities. All right, and what you find after some algebra that I invite you to do maybe with Mathematica or other software is that this is given by G effective mt, so a kind of non-analytic structure, okay, multiplying the mass. Okay, this is the energy density. Why are we following all this? Because we want to understand with precision how the particles behave as the universe expands. Okay? So this exponential separation is very important. It's one of the key points of this section. The reason why this is so, this is called the Boltzmann factor, and represents the idea that you are in a thermal bath. So remember that all this is in equilibrium. We are assuming that there is equilibrium configuration in the early universe. If the mass is much bigger than T, okay, it is very hard for these particles to be produced out of the bath. Okay, so it's very easy for them to decay, but very hard to be formed. So they're going to be exponentially suppressed. So the typical energy density for m much smaller than T, rho goes to 0 very fast in equilibrium. Okay, again, that means that if you are in equilibrium always in the history of the universe, all massive particles should disappear. But we know that some massive particles are around us. That means that at some point equilibrium should not be efficient if those are going to be around us for some time. This is important both for standard model particles and for dark matter particles. So let's now understand when this equilibrium and non-equilibrium happens. And for this, we need to start exploring rates of dark matter annihilating or converting into standard model or other particles. Okay, so I'm going to take a sip of water. Okay, and to understand when this happens, what we need to do is to understand which process is keeping things in equilibrium. Okay, so imagine that this process is a dark matter plus dark matter interacting such that you generate standard model plus standard model particles. So something like matter. All right. So this reaction will have some rate, which is going to be given by cross section, velocity of dark matter, and then number density of dark matter. That's where we are going to be using the fact that since we are in an expanding universe, this quantity here evolves with time. So if gamma was that the rate keeping things in equilibrium was bigger in the past, at some point, because n goes to, it tends to go to smaller values, gamma also depends on time, and it decreases with time. As it decreases, it may decrease so fast that things are no longer in equilibrium. When does that happen? Well, the thing is that the universe is expanding, so things have to interact with each other. So if the rate of expansion is bigger than the rate of the reaction, that's when you leave equilibrium. So that means that if gamma is much bigger than h, remember h is, I didn't define it, I think, yeah, h is defined as the rate of expansion, a dot over a. In this case, there will be equilibrium. In this case, equilibrium will start to be lost, and when gamma is much more than the expansion rate, let's say that particles don't have enough time to interact before the universe is expanding by a considerable amount, so equilibrium is lost. If equilibrium is lost, that's good for us. Why? Because in equilibrium, if you have a massive particle, it disappears very fast. But out of equilibrium, so if particles don't interact, how do massive particles evolve? So massive particles, remember we saw this before, evolve according to the law that this is, they disappear but slower. So they don't disappear from the bath, they just dilute. Okay, so the number density out of equilibrium is given by this number. So I guess you get the idea that we want particles to evolve first in equilibrium to produce them in the idea that everything is interacting with each other. But if they are massive and their mass, there's some time when the mass is of the order of temperature, then the temperature drops so much that they will disappear unless at some point they are out of equilibrium, and then the number density, this number density, will not fall so drastically. Okay. To be able to predict this, we need some extra tools. Okay, I'm gonna write the beginning in the last 2 minutes I have for today, and we will continue tomorrow. All right. So what we want to understand is the evolution of the total number of particles, so number density multiplying by a cube as a function of time, and this is going to be given by new particles per unit time minus lost particles per unit time. Okay, so how many new particles we're going to have? Well, that is where you have to put the reaction that you are exploring. So if there is a diagram of this form, the one we had before, dark matter going to a standard model. Now, I did it the way around just to make connection with figure 10. So this is what happens, with dark matter annihilated into a standard model. That here you have to put the rates of these processes. So I'm going to write it very fast. I explain it tomorrow. Okay, so it's going to be, you have to integrate over phase space of one particle, phase space of second particle, phase space of A, phase space of B, this is 1, 2, A, B. Here there is a standard delta function of conservation of momentum plus PB minus minus P1 plus P2. And here it is, you have to put precisely the rate of 1, 2 to AB square, right? That's the rate. This is the matrix element, and multiply by, oops, what happened here? Multiply by what? By the distribution function. So number of particles of 1 at the beginning, number of particles of 2 at the beginning per unit volume, and you have to take into account that these reactions are either enhanced or suppressed if there are fermionic or bosonic degrees of freedom. Okay, those are the particles which are created, and those that are eliminated are share the first part of this integral, but now you have to write the matrix element for the opposite process. And we continue here in the next lesson. Okay, thank you very much, and I hope that this is getting more and more interesting for you. All right, yeah, I need to plug here everything, and see you tomorrow.